Hello, my curious old beans. Did you know that all potentially living planets, like the Earth, are most likely also inhabited according to the rule of carbon chauvinism? If there is life there, of course. Why is only carbon considered by scientists as something fundamental for the beginning of chemical evolution? Well, I have a couple of interesting explanations for this. Let's start with the fact that carbon chauvinism appeared for a reason, and life on our planet is literally based on carbon and the elements that are in the periodic table next to it. These elements are small in size and are able to create sufficiently strong covalent bonds between themselves. You all know these elements perfectly well, I hope. Alright, these guys. These are in fact carbon, nitrogen, oxygen, phosphorus, fluorine, and sulfur. I mean sulfur. Freudian slip. Okay, there is also hydrogen, of course, but it is a bit like an exception here. I will not frighten you with excessive complex chemistry. In general, he's like an exception, but not an exception. There is something difficult. As you know very well, I hope, the skeleton of all organic substances and biopolymers is certainly carbon. This is a fairly stable substance with an equally stable atom, which can form four covalent bonds with other elements. At the same time, these connections are quite strong, which often underlies the creation of biopolymers. Any polymer can always be disassembled into separate pieces. For example, each amino acid has a carbon skeleton, at one end of which there is a hydroxyl group, at the other an amino group. Thus, the amino acid itself, due to the bonds between the atoms, is a stable monomer with separate groups of atoms at both ends for chemical interactions. These same groups of polypeptides form the so-called peptide bonds. At the same time, the energy of these bonds is relatively low, which makes it possible to constantly assemble and disassemble new proteins from individual amino acids with a relatively small expenditure of energy. That is, it is often not necessary to synthesize amino acids from scratch every time, just as it is also not necessary to disassemble the proteins obtained in the process of nutrition by atoms. This is very convenient. As you well understand, I hope, this saves a lot of energy. In addition, carbon is able to create double bonds, which allows you to give the resulting molecular additional properties, expanding the methods of subsequent chemical perversions. Well, the skeleton is clear. Carbon creates a chain from itself. The chain is stable. The main bonds between monomers inside a biopolymer are provided by atoms of other substances, whose binding energy is slightly lower. Thus, the carbon skeleton itself remains unaffected during disassembly. This is energetically advantageous, but in addition, carbon has another important property. Here we need to remember about silicon. If you pay attention to the periodic table, you will see under the carbon its closest relative, silicon. Actually, this good dude and his properties are quite similar to carbon, even though they are. But silicon has one problem. The bonds that it forms are weaker than carbon because its atom is larger, and the substances obtained from it often require either special conditions or strictly low temperatures. There is also a need to cheat with pressure. In general, it is difficult. And some of these substances, for example silan and other analogues of hydrocarbons, generally burn immediately upon contact with oxygen, and without exceptions. The temperature range of the reaction in silicon life is incredibly small, and with oxygen it is deadly. But oxygen is one of the most common elements in the entire universe, and especially on Earth-type planets. Another problem is connected with oxygen. If carbon burns in oxygen, the carbon dioxide will turn out a substance that is only slightly soluble in water and at the same time quite easily destroyed. That is, carbon from this gas is quite easy to return back to chemical reactions. Well, for example, plants do this. But when silicon is oxidized, quartz, or simply sand, is formed. So, hypothetically, Silicon Life, like Bender from Futurama, should shoot with the bricks. And everything will be fine, but silicon oxide is a very stable chemical crystal. In addition, it is also refractory. Well, silicon itself, in any case and anywhere in the universe, will quickly oxidize and go into a chemically inert precipitate. This will be the end of the attempts to evolve silicon life, because all the silicon will go into stones. In addition, if you send spectrographs into space and look at the chemical composition, I don't know, nebula for example, then you can notice one sad moment for fans of silicon life. We found everything in outer space from nucleotides and polysaccharides to relatively complex polymerides and even ethyl alcohol, while silicon-containing substances are known in an amount of 10 pieces at most, some of which have only 2 atoms in the molecular and one of them is silicon, as for example in silicon carbide. In general, it is not diverse. So, life most likely has no other options but to be collected on the basis of carbon. There is nothing else. And I'm still silent about the ability of carbon to create cyclic and heterocyclic compounds. Well, okay, it's clear with carbon. It has just turned out to be the most successful in terms of chemistry and physics within the framework of our universe. But what about water? Water has many biogenic properties, but there are 3 of them that are the main ones. Well, maybe 3.5. We'll talk about this a little bit later. First, water is a good solvent due to the properties of its molecules. And this is important because organic reactions go fast in solution. The molecules are actively moving and nothing stands still. Secondly, water has a huge heat capacity, which allows you not to be afraid of freezing. The water will always have a certain inertia, and the climate will not suddenly become too warm or too cold. Remember how, for example, ocean currents work. And the third thing is that water does not deposit its solid fraction to the bottom when it freezes. At the reservoir, only the surface freezes, which in a compartment with a high heat capacity save the aquatic population from death and freezing through. Well, here is the property number 3.5. It is very important that in the conditions of our atmospheric pressure, water has a fairly wide range of temperatures at which it is a liquid. This, by the way, is also quite an important point. Although, of course, water also has its drawbacks. Who doesn't? For example, when it freezes, it forms a mirror and white ice crust, which actively reflects solar radiation back into space. Thus, under certain conditions, the entire planet can become a snowball, which in fact was actively practiced by in the Cretaceous and Archaea when life didn't yet have such an impact of the climate. And now, the main thing is that most of the currently possible solvents do not have the necessary properties to replace water. Some of them are not sufficiently electrically neutral, while others exist in the liquid phase only for a short period of temperatures. Others have either an acidic or an alkaline environment. And the most ridiculous thing is that as a solvent, water can only be replaced by liquid ammonia, sulfuric acid, and suddenly carbon dioxide. But liquid ammonia is harmful for many biopolymers, sulfuric acid and even more so, and carbon dioxide. Well, this is one of the most ideal candidates, an ideal solvent with a low viscosity, while the reactions that we usually carry out in aqueous solutions with organic matter in liquid carbon dioxide go 10 times faster. Magic? Well, yes, almost, but there is also always one but. Carbon dioxide becomes liquid only at gigantic pressures. For example, as in the Mariana Trench, where in fact bottom lakes of this substance were found. And yes, there is life right there in the lake of carbon dioxide. You just need to change the protein composition on the membranes a little, and that's it. Save the DNA, and everything else will live in such water. Well, of course, water in quotation marks. Life there is unicellular, like the songs of Nicki Minaj. And from this comes a rather interesting point. Aliens most likely will not look for life on Earth if they fly past our solar system. After all, it turns out that our planet is too warm and unstable climatically. It has a weak atmosphere, very low gravity, and the pressure is unimpressive. And therefore, none of the described cool substances, such as ammonia or liquid carbon dioxide, can exist on their surface in the right amount. So, according to the aliens, there is probably no life on Earth. But the worst thing is that even if there is intelligent life on another planet, we will never meet them. These creatures simply will not be able to leave their planet. After all, they are highly likely to live on a super Earth with high gravity, where all this liquid carbon dioxide just exists. But there are no such rocket engines to gain the necessary space speed and fly out of the atmosphere of this planet. So, chemistry can safely leave us alone in cosmos, even if it turns out to be as densely populated as possible on every corner.